It's the Learning Zone on BBC Two. And the final sequence this morning is the Open University, which includes natural navigators and an exploration of the ocean floor. First, see how the behaviour of the enormous variety of chemical elements can be understood using the best known of scientific tools, the periodic table.
Everything you can see around you is made of atoms, and there are about 100 different kinds of atom in all, the atoms of the chemical elements. The chemical elements can be marshalled into groups or families whose members resemble one another, and for a scientist, this idea is tremendously important. But whenever I think about the chemical elements, what strikes me first is not any pattern or similarities in their behaviour, but their incredible variety. Let's look at some examples. Here's a chemical element, oxygen.
The bubbles on the leaves of this plant are oxygen. It's a colourless, transparent gas. It's because air contains some oxygen that our fires burn. If this splint is tapped out, the oxygen in the jar rekindles it. To stay alive, we have to breathe oxygen gas. But this element, chlorine, is a gas that we mustn't breathe. It was the first of the war gases. In the First World War, thousands of men were killed or maimed in chlorine gas attacks.
There are two more chemical elements in these balloons. The red one contains hydrogen, the yellow one, helium. They're both colourless, transparent gases, and both are lighter than air. Because of this property, both elements were once put to a particular use, and they still are at fairgrounds.
But in their chemical behaviour, hydrogen and helium couldn't be more different. Hydrogen burns with a fiercely hot flame.
Burst into flame. Wait, get it started. It's bright and it's bright. It's bright and terrible. Oh my, get out of the way, please. It's burning, bursting into flames, and it's falling on the mooring mast, and all the folks between us. This is terrible. This is the worst of the worst. Oh, it's running. Oh, 400 or 500 feet into
Disasters
the sky.
like this would never have happened if helium had been used instead of hydrogen. Helium doesn't burn. Indeed, it doesn't react with anything. So today's manned balloons are lifted by helium. But most of the chemical elements are not gases, but solids. A few solid elements are non-metals like sulfur, which sometimes occurs beside volcanic springs.
These two probes are wired to an electric bell. I can use them to find out if things conduct electricity. Now here's a very handsome looking lump of sulfur. I'll touch the probes across it. Well, that doesn't ring any bells. Sulfur is a non-metal, and non-metals hardly ever conduct electricity. Now here's a lump of aluminium. Aluminium is a metal, and metals are good conductors. Now, most of the solid elements are metals like aluminium. Yet even among the metals, there's great variety of behavior.
Mercury is a liquid at room temperature. Cesium melts in the hand. To melt iron, you need a furnace as hot as this. And much higher temperatures are needed to melt this element, tungsten, the metal with the highest melting temperature of all.
Yet amid all this bewildering variety, there is a pattern, although it's quite hard to find. Scientists call this pattern the periodic law. Whenever it's mentioned, the name of one man springs instantly to mind, a man born in 1834 amid the forests of Siberia, Dmitry Ivanovich Mendeleev. At the March meeting of the Russian Chemical Society, 1869, I communicated a paper on the correlation of the properties and atomic weights of the elements. The substance of this paper is embraced in the following conclusions. 1. The elements, if arranged according to their atomic weights, exhibit an evident periodicity of properties. Today, we use atomic number where Mendeleev used atomic weight. But what did Mendeleev mean by periodicity of properties? Let's try to find out by laying out the elements as he laid them out in this book.
We'll ignore hydrogen and start with element number 2, helium. The 8th element in this row is fluorine. Next comes neon. Now, neon resembles helium in two very obvious ways. First, it's a gas, and second, it doesn't react with anything. We'll mark this similarity by putting neon underneath helium. Off we go again. Another row of 8, and we get a sign that we're on the track of something very fundamental. The next element is argon, and again, it's a gas which doesn't react with anything. So argon goes beneath neon, and off we go again. Let's stop there at scandium. The vertical columns of this arrangement are called groups, and the horizontal rows are called periods. What we have here are the beginnings of a periodic table. The groups are numbered from 0 up to 7. The most important thing to remember about the periodic table is that the groups contain elements which resemble each other. Let's look at the elements of group 0, the noble gases. When it's complete, it contains 6 elements: helium, neon, argon, krypton, xenon, and radon.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it. The elements in a group are similar, but of course they differ from one another too. And those differences often correspond to some sort of regular change as we go down the group from the top to the bottom. To see these things, let's look at the elements of group 1, the alkali metals.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
And that seems a convenient point to break off our study of the alkali metals. The groups contain similar elements. That's the most important thing to know about the periodic table. The next most important thing is that trends or regular changes occur as we move across a period. To demonstrate this, we use this period, the one that runs from neon to chlorine.
We'll look for a regular change by reacting these elements with this element, fluorine. Fluorine is the Tyrannosaurus rex of the chemical elements. It reacts, often ferociously, with nearly all the others. Now neon, the first element in the period, is a noble gas. Even fluorine won't react with that. That's a pretty flat beginning, but don't worry, things will soon warm up. The next element is sodium. Fluorine gas is delivered through the tube on the left. See how violent the reaction is. We'll react magnesium in the same way. Now for aluminium. This time, we'll tip aluminium powder into a jar of fluorine gas. We'll try silicon in the same way. With phosphorus, we'll go back to using a stream of fluorine. And with sulfur, we'll show you both methods. A flash and a burn.
It's hard to believe that among that series of fireworks there was a regular change, but there was. If you just stand and peer at the reactions, you miss it. But you see it if you look at the formulae of the compounds that are formed. Let's look at the number of atoms of fluorine that one atom of each element combines with.
Neon, 0. Sodium, 1. Magnesium, 2. aluminium 3, silicon 4, phosphorus 5. In each case, the products of the reaction are the highest fluorides of the elements. The number of fluorines increases in steps of 1 from neon to phosphorus. So, what formula would you predict for the highest fluoride of sulfur? If you said SF6, that's right. Fluorine reacts with sulfur to form sulfur hexafluoride. Now, what would you predict for chlorine? I expect you said ClF7. Well, there you were unlucky. The highest fluoride is in fact ClF5.
This failure is just one instance of a very important limitation of the periodic law. Very often, periodic trends are neither as precise nor as regular as we would like them to be. But those trends are there all right. Let's look at another one in the neon chlorine row, the one in which Mendeleev himself put so much trust, the trend in the formula of the highest oxides. We'll start by showing you some reactions in which those oxides are formed. First, aluminium. If aluminium powder is tipped into the flame of a gas burner, the aluminium burns in the oxygen of the air. The white fumes are the oxide of aluminium, Al2O3. Now, let's take a look at another element in the same row, phosphorus. This is phosphorus, burning in oxygen. We started off in the dark, so what you're seeing is by the light that the phosphorus flame alone provides. The white fumes are the oxide of phosphorus, phosphorus pentoxide.
Al2O3 and P2O5 are just two of the highest oxides of the neon chlorine period. This time, we have to do a little arithmetic to see the trend. What we want is the number of moles of oxygen atoms that 1 mole of our element combines with. Let's start with neon. Well, of course, neon is a noble gas. It doesn't react with oxygen. So, our number is 0. The next formula is Na2O. 2 moles of sodium atoms combine with 1 mole of oxygen atoms. So, each mole of sodium atoms is combined with half a mole of oxygen atoms. So our number is 1/2. If we do this calculation for all the oxides, we get a number that increases in steps of 1/2 as we move across the period. This time, the trend is perfect.
This emphasis on the formulae of compounds, on the ratios in which atoms combine, on what Mendeleev knew as the valences of the elements, lies at the heart of the periodic law. Without it, the law would often seem ridiculous. For example, look at these elements. Silicon and carbon. They lie at the top of group 4. One form of carbon is diamond.
Now, you may have read somewhere that diamonds are forever. After you've seen this, you'll never believe that again.
So, when diamonds burn, they form a gas. As you can see, it's quite heavy. Now, we could have burnt silicon in the same way, but the product wouldn't have been a gas. It would have been this. This is the oxide of silicon. It's some sand that I picked up on a Norfolk beach. So, when carbon and silicon are burnt in oxygen, the products look completely different. They have completely different structures too, but they both have the same kind of formula. They're both dioxides. In both compounds, there are 2 oxygen atoms for every carbon or silicon atom. And it was this similarity in the formulae of the highest oxides that led Mendeleev to put carbon and silicon in the same group. This emphasis on the periodicity in the formulae of compounds explains the form of Mendeleev's table. It explains not only its strengths, but its weaknesses too. In the hands of Mendeleev and his supporters, his table eventually took on this form.
Now, it's the weaknesses in a theory that can lead us to better things. So let's look next at 3 weaknesses that this table has got. First of all, lower down in the table, most groups split into 2 separate columns, the A and B subgroups. The difference between the elements of the A and B subgroups is often so great that it doesn't seem right to include them in the same group. Group 1 is a good example. Let's compare these 2 sets of elements. We'll start with a reaction that you've seen before. Here are lithium, sodium and potassium reacting with water. Now obviously you wouldn't want your wedding ring to behave like this when you were doing the washing up, and of course it doesn't. Neither gold, nor silver, nor copper reacts with water at all. For weakness number 2, take a look at group 8. This turns up intermittently lower down in the table, and when it does, it contains 3 elements, not 1. This had to be done to preserve periodicity elsewhere in the table. Group 8 is a rubbish tip, a graveyard for elements which don't fit. And there's an even worse example down here. This sad-looking footnote contains 15 so-called rare earth elements. They were supposed to occupy this one space marked by an asterisk in group 3. There is some justification for this. Nearly all 15 elements have highest oxides of the group 3 sort. But 15 elements in one box is a little hard to swallow.
So can we design a better periodic table, one in which these weaknesses disappear? We can if we use a distinction that I touched on at the start of the program, the distinction between metals, semi-metals and non-metals. Let's look at the distribution of metals, semi-metals and non-metals in our Mendeleev-style table.
We've coloured metals green, semi-metals yellow and non-metals blue. You can see that it's a mess. There isn't any obvious pattern in the distribution, although metals appear mainly on the left of the table. Now for a jigsaw puzzle. To begin with, the rules. Whatever changes we make, first, elements which started in a column must stay in that column, and second, the order of atomic numbers must be preserved. Now for the problem. The table must be restructured so that we get a periodic distribution, so that in any row, metals appear on the left and non-metals on the right, with semi-metals in between. Let's go. Now we'll add the remaining elements in the last row. This is the result, today's preference, the long form of the periodic table. The A and B subgroups have been separated, and each space contains only 1 element. There are no footnotes and no graveyards.
The long form of the periodic table was first worked out by thoughts and methods not too dissimilar from the ones that we've used in this program. Once invented, it was used by physicists such as Niels Bohr to guess the electronic configurations of atoms. This was possible because the periodicity in electronic configuration is best represented by the long form of the table. So, the periodic law didn't just bring order to the chemistry of the elements. It also helped solve one of the most fundamental of scientific problems, the problem of the inner structure of the atom. You can look long and you can look hard, but it's not easy to find other scientific achievements that have been as fruitful as that.
Now on BBC Two, the Open University takes a look at the natural ability of animals to navigate.
This balloon carries a passenger beginning a journey that will tell us more about animal navigation. Ken Abel from the University of Albany in New York State studies navigation in white-throated sparrows. These birds fly south to winter in New York and return north to Canada in the spring. They migrate